Okay. So section 4.1, solving systems of linear equations. Our learning objectives are as follows. We have determine whether an ordered pair is a solution of a system of equations. And then the two different methods are being able to learn how to solve by utilizing our substitution property. And then also our second method is by using elimination. So first, we have what our formal definition of a system of linear equations is. And that's just essentially two separate linear equations. Right now, we're looking at two linear equations in standard form, but they can be in slope-intercept form, aka our y equals mx plus b. They can be in point slope form, aka y minus y1 is equal to m in parentheses x minus x1, or they can be in standard form, some version of x plus some version of y is equal to our constant, some number. This slide is very wordy, but I am going to ask some students to read them or read the paragraphs for me. So let's see. I'm going to choose Edith. Do you think you can read the first paragraph for me? And then Adriana, I'll have you read the second for me.
A linear equation is in two variables such as 2x plus y equals 7 has an infinite number of solutions. Its graph is a line. Remember, every point on the line is a solution to the equation, and every solution to the equation is a point on the line.
Thank you. And then Adriana.
To solve a system of two linear equations, we want to find the values of variables that are solutions to both equations. In other words, we are looking for the ordered pairs x and y, x, y that makes both equations true. These are called the solutions of a system of equations. To solve a system of two linear equations, we want to find the value of the variables that are solutions to both equations. In other words, we are looking for the ordered pairs x, y to make both equations true.
Beautiful. Thanks. And so now we have, again, our formal definition. Solutions of a system of equations are simply the values of the variables that make all the equations true. So if we were going back to this sample example, we would have an ordered pair in the form of x comma y that makes both the first and second linear equation true. And once again, I stated this on the previous slide a second ago, but that ordered pair is always in the form of x comma y. So now knowing this, let's give this example one a shot. All we want to do is determine whether the ordered pair is indeed a solution to this system of equations. So part A, we're going to test the point -2 comma -1. And how do we do this? Well, first, we're looking at x minus 1 is equal to -1, and we want to make those substitutions. Wherever you see an x, we're placing in -2. So we have -2 minus, and wherever we see a y, we are placing in a -1. Is this indeed equal to -1? And we test that out. Let me maybe color code some of this so you guys know exactly what's going on. And so now when we simplify this, two negatives next to each other give us a positive. So -2 plus 1 gives us -1. And is -1 indeed equal to -1? It is. So we know that our -2 comma -1 works for the first equation, but we're not done with part A because we have to test that second equation too. both of them have to work in order for it to be a solution. So now, once again, wherever you see an x, we're going to replace that with our value of -2. And wherever you see a y, we're going to replace that with the value of -1. Is this indeed equal to -5? I'll color code once again so that you guys can clearly see it. Now we're just going to simplify. We have 2 times -2 is -4. Two negatives next to each other once again gives you a positive. And -4 plus 1, does that give us -5? Well, -4 plus 1 is actually -3, and -3 is not equal to -5. So what can we conclude on this part A? Therefore, -2 comma -1 is not a solution to the system. Now let's take a look at our part B. The new point that we want to test out is -4 comma -3. So same exact process, it's just different coordinate points. Our x in this case is -4. Our y is -3. Is this indeed equal to -1? And I'm not going to color code this time so that you guys have to pay a little closer attention. Two negatives next to each other give us a positive, and so we have -4 plus 3. Well, -4 plus 3 gives us -1. So once again, that first linear equation indeed works. But we need to test the second one as well. So we have 2 times -4 minus -3. Does this indeed equal -5? Two negatives next to each other give us a positive. 2 times -4 is -8. -8 plus 3. Does this indeed give you -5? It does. So what do we have? We have a solution. How do we write this? Therefore, -4 comma -3 is a solution to the system. And then we're done. Let's go to the next slide. And I'll take attendance a few times throughout the class, just so that I know who's sticking with me throughout it all. Okay, example 2. Determine whether the ordered pair is a solution to the system. So same exact procedure, we just have different linear equations and we have different points. We're going to go through this a little faster now that we have a good solid foundation. So part A, we have our first equation is 3x plus y. Our x in this case is 1. So 3, 1 plus -3. Is this equal to 0? 3 minus 3 equals 0. Good. Second equation, we have 1 plus 2 times -3. That's our y. Is this equal to -5? We have 1 minus 6. Ooh, that is equal to -5. So 1 comma -3 is a solution to the system. Now let's look at our point 0, 0. Wherever you see an x, we're going to plug in 0. Wherever you see a y, we're also plugging in 0. 0 plus 0 does indeed give you 0. So that first equation works. Second, 0 plus 2 times 0. Does that give you -5? It does not. Because that left-hand side ends up shooting to 0, and 0 is not equal to -5. So therefore, our point 0, 0 is not a solution to the system. Okay. Let's move on. These are our formal notes for solving a system of linear equations by utilizing our substitution method. Essentially, what you want to do is you want to choose an equation from that system. So either your top linear equation, like we have here, or your bottom one, and you want to solve for a specific variable. I personally always like to look at the two equations and see which one's easier, which one is already separated on its own so that we can easily solve for it, or has a coefficient of 1 so that we could easily solve for it. And then from there, what we're going to do is we're going to take that value. So for example, we end up getting y is equal to something. We're going to take whatever it's equal to, and we're going to grab that grouping and plug it into that variable in the second equation, and then solve for the variable that's left. So it sounds a little confusing right now. I am going to show it or show how it's done through this concrete example, which in this case is example 3. Lucky for us, this system of equations here already has y all by itself. So what we should do is, wherever you see a y in that second equation, that's where we are going to fit in our whole 2x minus 1. Okay. And so we have y is equal, or sorry, we have x plus 3, big giant parentheses, because this is where we're fitting in our y, and we have y equal to 2x minus 1 from that first linear equation. And then we'll finish up the second is equal to 10. Now, what did we do? Well, we put our two equations together so that we are now looking at just one equation that we, or I should say, one variable that we can solve for. So now it's just straight back to our distributive property as well as some inverse operations in order to simplify. Let's go ahead and add 3 to both sides. X is the same as 1x. 1x plus 6x is 7x. 10 plus 3 is 13. Let's divide 7 by both sides. So we get our value of x to be a fractional result, which is 13 over 7. We are not done though, because we need to now figure out what our y-coordinate point is. Just like in examples 1 and 2, our final solution to the system is in the form of x comma y. We only have our x-coordinate point. We still need to find our y. So we're going to utilize that first equation once again, because y is all by itself. We don't have to do the first equation every single time. We can plug this into our second equation and solve for y. It's going to take us a few extra steps, and Mathematicians are inherently lazy, so we always want to figure out what's the quickest way to get to the result. 2 as a fraction is just 1. And then we have 2 times 13 gives you 26. 1 times 7 is 7. 1 as a fraction is 1 over 1. But if we want to turn this to have a denominator of 7, we should multiply it by our fancy form of 1, which is 7 over 7. So we get 26 minus 7 over 7. 26 minus 7 is simply 19, because now we can just subtract the numerators since the denominators are the same. There's a common denominator, and we solved for y. So ultimately, in coordinate form, x comma y, we end up with 13 over 7, comma, 19 over 7 as our solution to this system. And we're done. Any questions at all? Josh, do you have a question? Or no? No? Okay. All right, so let's keep going. Example 4 is another example where we want to practice our substitution. So in this case, unfortunately, we're going to have to do slightly more work, and that's because none of our variables are all alone. But if you look at the 2 different equations, you'll notice that the bottom has a coefficient of 1 for that y. So I'm going to go ahead and solve for y all by itself using that bottom linear equation. I'm actually going to just add y to both sides, and then I'm going to bring that 8 over to the left-hand side. So we're essentially looking at just y is equal to 6x minus 8. Now that y is all alone, let's go ahead and highlight this. Wherever you see a y in that first equation, we're going to plug in our 6x minus 8. So we have 4x plus 2, so big giant parentheses, this is equal to 4. And inside these parentheses, you are going to fit in your whole 6x minus 8. Once again, we'll be utilizing some distributive property, inverse operations in order to simplify and solve for our value of x. So we have 4x plus 12x minus 16 is equal to 4. Let's combine some like terms here. See 4x plus 12x, and then we're going to go ahead and add 16 to both sides. Four plus 16 gives you 20. And so we have 16x is equal to 20. Did I make a mistake? Oh, yes, I did, right? It shouldn't be 4x, it should be 6x. Thank you. Thank you for paying attention. Yeah, anytime I make a mistake, either just unmute yourself or write it in the chat. So that's 6x. Wait, did I make a mistake? No, we're using the top one, right? 4x plus 2y. Yeah, no, that was all right. Double check. Oh, you were just asking to explain the first part again. Okay, let me solve for it and then I'll run through the explanation one more time. So everything was correct. Our last step is to divide both sides by 16. And then we end up with x is equal to 20 over 16, which you'll notice you can simplify this fraction. Both 16 and 20 share a factor of 4. 4 goes into 20 5 times, and 4 goes into 16 4 times. So we get our x value to be 5/4. So the first part, I'll explain again. How did we essentially get to this? Well, whenever we first look at a system of equations, what we want to do is we want to look for the easiest option in order to solve by substitution. And so this second equation here, we notice that one of the variables has a coefficient of 1, really -1 here, but that still helps us out. So I want to work with this equation to isolate that y all by itself. Isolate it and get it positive. So what I did was I added y to both sides, and then I subtracted 8 to both sides so that I manipulated this equation for it to become y is equal to 6x minus 8. Now from here, y is all by itself. And the whole concept of substitution method is substituting in a variable into the other equation in order to solve for that remaining variable, which is exactly what we did in this second part. We substituted wherever we saw a y in that other equation, we substituted in 6x minus 8 so that we turned the equation into a one variable equation. Why did we do that? Well, whenever we have a one variable equation, we are now able to solve for that variable. And we did so using our basic algebra, our distributive property in this case, and our inverse operations. We were able to figure out that our x value is 5/4. We are not done though, because now we need to solve for the numerical value of y. So we're going to go back to this chunk that we started with, and now wherever we see an x, we are going to fit in our 5/4, which we solved for a little earlier. And now let's once again simplify. 6 as a fraction is 6/1. 6 times 5 is 30. So we get 30/4. And 8 with the denominator of 4, we need to multiply by 4/4. So we're looking at 32/4. 30 minus 32 is simply -2/4, which is just simplified to -1/2. So all in all, we end up getting our coordinate point to be 5/4, comma, -1/2. Is a solution to our system. And we're done. You understand it now? Nice. Students are direct messaging me, so I'm not talking to myself, I promise. All right, let's go to the next slide. And now we're on to elimination method. So these are the formal steps for solving a system of equations utilizing elimination. What you're essentially doing is you keep your system of equations in that sort of stacked format, and you want to multiply either one or both of those equations in order to make the coefficients opposite of one another. And why do we want to make them opposite? Well, for example, let's say we're looking at 2x, and then the opposite, it's negative 2x in that second system. If we add those two together, they'll cancel out and they'll be eliminated from our systems of equations, which means we'll be able to solve for that variable y. I am indifferent at this point in my life with substitution and elimination, but when I was your age, I definitely favored substitution more. There are situations where elimination is the way to go because you'll be able to solve for your system much faster. But I will say, once you do that cancelization, you can easily solve for one of the variables, but then to find the remaining one, you have to go back in to either one of the equations. Whereas with substitution, which will go back here, once you take care of the substitution portion, you don't really have to go back into both of these. You can just go straight back to the work that you did with isolating one of those variables in order to easily solve for your y. But there are pros and cons to both. All right, why don't we go and practice an example involving elimination now. And so we're dealt with this system of equations. I always like to keep an eye out for if there are any pluses or minuses taking place. And I see in the y's, we have a plus 2y and then we have a minus y here. So what I just have to do to this bottom equation is to multiply it by a positive 2. I have to multiply the entire equation by positive 2. And when I do that, it manipulates this into our negative 2y, which will cancel it out. So I'll just write the equations again over here so that you can still see what we've started with in the beginning. And minus y is the same as minus 1y. And so we plan to multiply that second one by positive 2. And so when we do that, nothing is happening to that first equation. So I'm going to just keep that as is. But that second one is now being manipulated into 4x minus 2y is equal to 6. You have to multiply every single term in order to keep it balanced. Now, you can easily see that 2y and negative 2y cancel out because what we're doing is we're adding these two equations together. 3x plus 4x gives you your 7x. And then you get 12 plus 6 gives you 18. Our last step is to divide both sides by 7. So we end up with x is equal to 18 over 7. So it's always, in a lot of cases, it's much easier to get one of the variables' numerical value, but it's the second portion that will take a little extra step. So we still have to solve for our y. And when we look back on our two systems, I think the easiest one to plug into is that 2x minus y is equal to 3. Because what we can do is we can add y to both sides and then subtract 3 to both sides. So we're looking at y is equal to 2x minus 3. And now that the y is all alone, we can simply look at our x and plug in that 18 over 7. So we have y is equal to 2 in parentheses 18 over 7 minus 3. 2 as a fraction is 2 over 1. 2 times 18 is 36. over 7. So we want to find a common denominator, which in this case is 7. Multiply 3 over 1 by 7 over 7. And we end up with minus 21 over 7. 36 minus 21 gives you 15, I believe. So our y value is simply 15 over 7. What does this tell us? Therefore, put it in coordinate form. Cannot forget that step. 18 over 7, comma 15 over 7 is a solution to system. And we're done. Right. Let's tackle another example together. Just want to make sure these are two separate examples. Yeah. So we're still keeping the 3x plus y and oh no, they're completely different. That's great. Sometimes some of these slides have the same exact example, so I always just want to keep an extra eye out for that. All right. So what do I see here? Looks like we're going to have to do a little extra work, but not too much because we still have that plus or minus, which means I now want to multiply that first equation by a positive 3. When I do that, this becomes positive 3y, and those will cancel out. So let's reflect that on our paper. That second equation now is staying exactly the same. But that first equation, again, you're distributing that 3 to each of your terms. So you get 9x plus 3y is equal to 15. And then you're going to go ahead and add these both up. The plus 3y and the minus 3y are eliminated. That's why we call it elimination method. Then we get 9x plus 2x gives you your 11x. And then the 15 plus 7 gives you 22. These are some nice clean numbers. Divide both sides by 11, and then you simply get x is equal to 2. Great. But we're not done because we still need to solve for our y. Now, looking at our two equations again, I would say let's go with that first one because we can easily isolate our y by just subtracting both sides by 3x. And so now we're looking at just y is equal to 5 minus 3x. Now, wherever you see an x, we're just going to replace that with the value 2. 3 times 2 gives you 6. So we're looking at 5 minus 6, which gives us -1. And so what does this tell us? We have therefore 2 comma -1 is a solution to system. And we're all right. So substitution and elimination were the main methods taught in this chapter 4, which is actually all that we're learning out of all of our chapter 4, because our next lesson is going to be jumping to chapter 5 material. I am going to stop recording. So,